Good morning, everyone. It's my pleasure to introduce our first speaker of the day. Sherry Gong from Texas A&M University will be telling us about ribbon concordances and slice obstructions, experiments, and examples.
Thank you. Thanks for the introduction, and thank you so much for inviting me. It's pretty exciting to be here. Okay, so I'm going to be telling you about ribbon concordances and slice obstructions. So maybe to start, I'll just give like a little bit of a review of some of these concepts, just so that everyone's on the same page, though I'm sure almost all of you have probably seen this before. But so a concordance between two knots K1 and K2 in S3 is a cylinder F in S3 times 0, 1, such that its boundary consists of K1 and K2, right? So it's just a surface that is K1 on one end and K2 on the other. And we say that a knot is sliced if it admits a concordance to the unknot. And this concordance to the unknot, we're going to be calling a slice disk. And then the goal is to find slice knots and concordances between various knots, and also, I guess, to show when they don't exist. So like to basically we're just going to look through knots and see which ones have concordances to the unknot and which ones don't, and which two knots have concordances between each other. Okay, so in order to explain how we're going to find these concordances, what we're going to do is we want to think about decomposing concordances into more approachable pieces. So one thing you can do is, if you have a concordance embedded in S3 times 0, 1, in such a way that the projection to 0, 1 is a Morse function, then we can consider the critical points, minima and maxima, and saddle points of this Morse function. And what we're going to do is basically we're going to just try to construct concordances by piece by piece, by considering what it means to have a maximum, what it means to have a minimum, and what it means to have a saddle point. And just one other notion that I want to mention is that we would say a concordance from K1 to K2 is a ribbon concordance if it has no local minima. And we say a knot is ribbon if it has a ribbon concordance to the unknot. So basically you only have saddle points and maxima. This is I guess some people write concordance the other way, but just our concordances are going to be from the, heuristically from the more complicated knot to the less complicated knot. It's like a downwards concordance. This is basically because of the way we set up the computations later. So also just a little bit of background. So the reason they're called ribbon knots is you can think of them as an unlink with some ribbons attached. So something like this would be a ribbon knot, where you see the little orange components are the unlink, and you have some ribbon that sort of can intersect it can intersect itself, but somehow in a nice way. Okay, so there are a lot of conjectures about slice and ribbon knots. So one very classical conjecture is the slice ribbon conjecture, which says that all slice knots are ribbon. So what this means is if you have a knot and it has some concordance to the unknot, then it has to have a ribbon concordance to the unknot. And then you can ask a generalized version of this conjecture, which is if you consider concordance classes of knots. So if you take, all your knots, and then you consider two of them to be in the same concordance class, if there's a concordance between them, then you can ask, does each concordance class have a single sync? I'll sort of talk a little bit more about this later. There's also Gordon's conjecture, which says that if there's a ribbon concordance from K1 to K2, then K2 has to have smaller volume than K1. This is part of like a whole class of conjectures of this form. So basically the thing that, you know, the sort of heuristic behind this is that if you have a ribbon concordance from K1 to K2, you should expect K2, well, maybe you should, I don't know if you should, but you might expect K2 to have smaller everything than K1. So Gordon's conjecture says that it has a smaller volume. You could also ask, you know, like there are many notions of complexity for like knots, right? You could ask like all the like homology groups, like Chavanov homology, like knot floor homology. There are all these instanton floor homology. They're all like all these homology groups of knots, and you can ask that all of those be smaller. So Ian Zemke showed like recently a few years ago that that if you have a ribbon concordance from K1 to K2, then like all the homology groups of K2 are direct summands of the corresponding homology groups of K1. Well, I mean, I guess he showed this initially for knot floor homology, but like it has subsequently, like with the same method, been shown for like all of the, like, you know, things like instantons and like and Chavanov and basically all the other knot homologies. But you can ask, like, is that like a strict statement, right? Like, can they be equal, or like, does it have to strictly decrease? And then I guess, like, you know, there was a conjecture until like last year, which is that ribbon concordance is a partial ordering, so you can't have like a cycle. But you can actually still, in this case, still ask, like, is it possible? So the partial ordering just means that, like, well, okay, what Ian actually showed is you can't have like a cycle of ribbon concordances where K1, well, you can't have knots K1 and K2 such that K1 is ribbon concordant to K2 and K2 is also ribbon concordant to K1, where they're different, K1 and K2, but you can also ask the question, like, is it possible to have a non-trivial ribbon concordance from K1 to itself? I guess, like, there's always the trivial one, but like you can ask whether there's like a non-trivial one. So these are like all sort of questions of this nature of, like, you know, do you, when, like, we expect that for a concordance, ribbon concordance from K1 to K2, that K2 should be strictly smaller. There are also other notions of complexity you could ask, like you could ask, is the like, is the number of crossings of K2 smaller than K1, right? Like, there are just like a lot of notions of complexity, and somehow maybe we generally expect all of these to hold, that like just K2 just has to be in every way smaller than K1 if there's such a ribbon concordance. Okay, and then I guess, like, there are some obstructions to being sliced. So so, you know, if you're just trying to figure out which knots are sliced and which ones are not sliced or not ribbon, we have the Fox-Milner condition, which says that if you have a slice knot, then its Alexander polynomial can be factored as f of t times f of t inverse, f of 1 over t for a Laurent polynomial f with integer coefficients. This is actually, this condition is actually holds even for topologically sliced, which is a much weaker condition than, I guess in my talk, we'll mostly be talking about smoothly sliced. So this, like, this concordance in S3 times 0, 1, it's like smoothly embedded. But you can ask, like, so for like topology, you can ask the same thing topologically, and there's this condition that obstructs being topologically sliced. There's also signature. So for a slice knot, the signature has to vanish. This is also true for topologically sliced. Then there's like the Harold-Kirk-Livingston conditions, which say that there are twisted Alexander polynomials for P and Q, and these also have to satisfy a Fox-Milner condition. So this is like a bit of a stronger version than the original Fox-Milner. There's the S invariant. This is a concordance invariant that comes from Chavanov-Lie homology. It's just, you can just define it completely combinatorially. And yeah, so, and it's also like, it actually also provides a lower bound for the genus. So if a knot is sliced, that means it has genus 0. So the S invariant, like, has to vanish. And then there's also like various analogs of the S invariant from knot floor homology. So there's like the tau invariant and epsilon. They're just like a bunch of concordance invariants that come from knot floor homology that also obstruct sliceness. So this S invariant and tau, epsilon, etc. These are new. These are like all smooth, like they obstruct being smoothly sliced, but not necessarily topologically sliced. There's also SQ1 invariant for odd Havanov homology. This is a refinement of the S invariant corresponding to the first Steenrod square in odd Havanov. And this is also like, it's also a smooth, it's like a smooth obstruction. So it doesn't actually obstruct topological sliceness. And then I guess, so like, basically what our project was there are like 350 million knots of up to 19 crossings. And we're just trying to figure out which ones are sliced and which ones are not. So the method for finding ribbon concordances, like finding out if they are sliced, is like, well, we're really finding ribbon concordances between knots. So if, as I mentioned earlier, if you have a ribbon concordance, you can think of it in terms of saddles and maxima. So what that means concretely in terms of what we're doing is like, you think of the saddle point as an addition of a band, right? So if you go from like a knot and you have like a saddle, then you think of that as adding a band to your knot. And then you think of the maxima as like, a maxima is you're like capping off a component with a disk. So that's basically like just removing an unknotted, unlinked component. So you think of a saddle point as adding a band. So what we're going to do is we're just going to randomly add k bands, each of which increases the number of components. Certainly, when you add a band, like if it's like one of these saddle points in a ribbon concordance, it certainly has to increase the number of components, because if you add a band that doesn't increase, like if it keeps the same number of components, then that's actually going to give you essentially an RP2 or a Mobius band. Like that, yeah. So like that, like we're trying to find like cylinders, right? If you have a band that doesn't increase the number of components, that actually corresponds to basically an RP2, instead of like, it's like as if you added an RP2 to your cylinder, so that's bad. And then if you decrease the number of components, then what's really happening is previously you must have increased the number of components, and now you're decreasing them, so that's actually equivalent to like adding either a torus or a Klein bottle, depending on whether you decrease the number of components in like a compatibly oriented way to when you increase them. And that's also not allowed. We're just not allowed to add like RP2s or toruses, tori, or Klein bottles or anything like that. So each band that you add has to increase the number of components. And then what you want to do is check that like check if the result is a link. The resulting link can be decomposed as a knot. It is composed of a knot along with k unknotted unlinked components, right? Because basically we're saying you add k bands to create k extra components, and then if you actually have a ribbon concordance, then that means you should be able to cap off your extra components, and like capping off in S3 times 0, 1 really just means it has to have been an unlinked, unknotted like link component. So it's, itself is an unknot and it's not linked to anything else. And so if you can find such a thing, then that means you have a ribbon concordance from K to K prime. So here's some examples of like actually doing this. So you can see this, like this is some knot, I don't remember which one it is, but what we did was, you find like a band between two arcs, like that, and then you have to like, so you find two arcs that you can join with a band, and then you join them, and then you have to add some number of like twists to your band to, well, I guess to make sure you're actually doing a lot of searching, you should add, some number of twists, and also you have to make sure the parity is such that you actually increase the number of components. And like, I guess, there's like a lot of questions you could ask about how you would do this. Like, how many twists do you need, right? Is it like actually just like minus infinity to plus infinity, or do you want to like narrow it down? But like, and then like how you want to place the bands. So this is just an example where you have this knot, and then we add this band, and you can see, I guess, if you sort of like think about it a little bit, you can see that this lower, this bottom picture is actually the unlink. So this is an example of a ribbon concordance to the unlink, or to the, to the unknot, which is a ribbon disk. So here's a picture that's like a little bit more complicated, where you have to like, so we have, our band has to like, is like a little bit longer, right? It had to, I guess like usually what we did was we sort of went outward, starting with just like bands that like just are, connect two arcs that are next to each other, and then look for ones that dip under and over. So you have like here, you can see that these two arcs, like they're a little bit farther apart in the diagram, and then you have to like kind of, the band has to go, you have to like have some decision of whether you want to go under and over, but really what we did was we just checked all of them like up to a certain size. And then sometimes you need two bands or more. So in this picture, like, oh yeah, all of these pictures, by the way, are all like actually ribbon discs. So the picture on the bottom here is also the unlink. This one is again like, so this one is one where we needed two bands. We couldn't find a ribbon concordance that only uses one band, and so this one needed two bands. So you add, like you can see that, if you add those two bands, what you get is this picture on the right, which is, you can also sort of check this. I guess we helpfully colored the three components with different colors, and you can sort of check that this is in fact a three component unlink. So this is also a ribbon concordance. So I guess there's like, somehow like, I guess I gave like an algorithm, there's like a few optimizations you can do. So like, if you actually just check like all possible ways to, you can't really check all possible ways to add bands because there's infinitely many of them, but like, so like, but if you can just be like, I'm gonna add, like what we actually did, in fact, is you start with your original picture, and then you look at like bands that just by taking a path along, like from one arc, you just take like a random path along until you like, and then you attach it somewhere else. But by random, I don't actually mean there's randomness. We actually literally just checked all of them, like of up to a certain length of, and then like, but if you do like k of them like at once, that's going to be somehow like very time consuming. So what you actually want to do is add one band at a time, and then each time that you've added one band, there's some like things you can check, because if you add one band and you want to have a hope that like subsequent bands can take you to the unlink, then there are some conditions. Well, there's really one condition, which is that the link you obtained after one band is supposed to be a ribbon link. It's a link that such that it is concordant to the unlink. So there's like, we can check this. There are like a whole bunch of conditions. So one thing is like the linking number between the two components has to be 0. Like otherwise there's definitely no chance of like, of reaching like the unlink, because if you don't have 0 and you add more bands, you're still going to have linked components. The signature has to be 0. And then there's like a multivariate Fox-Milner test you can do on your link to see if it's a slice link. And yeah, so like there's like a few optimizations you can do of this nature. And then so I guess like maybe I'll tell you a bit about our results. So there are 350 million knots of up to 19 crossings. About 4 million of them satisfy the most basic like topological slice obstruction, like the most basic topological slice conditions we had, which were signature 0 and Fox-Milner condition. So for like the rest of the talk, I'm really only going to be talking about those 4 million. in theory, you could like, do this, like you could ask which knots are concordant to each other, even if you know that they're both definitely not slice. But there are like 350 million of these. So like, I don't know, that takes like a lot of computing power. So we really just like focused on the ones that had a chance of being sliced. So of these 4 million, we found that like about 2 million of them were not slice. And then like 1.6 million of them are ribbon. Like we found ribbon disks for them. And then there's like 18,000 that we still don't know. And then of the ribbon concordance, I meant concordance. Of the ribbon concordances that we found, there were like 1.2 million of them used one band. There were like 380,000 where we needed 2 bands. Like about 1.6 thousand used 3 bands, and then like 59 of them we used 4 bands. We also did like a 5-band search, but like did not actually find anything that like but that's not because you don't expect them to exist. That's just because 19 is not actually that many crossings. And then like, okay, but we didn't actually just like look for ribbon concordances to the other knot. We actually, within our sample of 4 million, looked for like every ribbon concordance we could find. And so the ribbon, so what we did was we made like a graph of like, if you look at a graph of all, of these 4 million knots that satisfy the basic conditions for topological sliceness, you can draw if you draw a directed edge from one knot to another, if there's a ribbon concordance from that knot to the other knot, then you just sort of look at this graph, then we found, I guess, 1.8 million concordances. So that's 1.8 million directed edges in this graph. And then in this graph, there were 1.6 million nodes with at least one edge, or nodes correspond to knots here, or with at least one edge going in or out. Mostly they're going out. In fact, almost all of them were just going out to something that had eventually leading to the unknot. As an undirected graph, it had 524 connected components with singletons removed. So that means there were 524 components that each had at least 2 knots in them. There is also obviously a few million that just where we didn't find any, they're concordant, or we didn't find that they were concordant to anything. And then one thing we found was that each component had a unique sink as a directed graph, like in our case. So what this means is you have so basically all the components kind of looked like this, where they all had a unique sink. If you sort of think about what the slice ribbon conjecture is saying, basically what it's really saying is that the component containing the unknot has a unique sink, because what would it mean for a knot to be sliced but not ribbon is if it's something over here where you being ribbon means you can just go these take downwards edges to get to the unknot. Whereas being sliced means if you take upwards or downwards edges, you can get to the unknot, right? So the slice ribbon conjecture is really saying that the component containing the unknot has a unique sink, so it doesn't look like this. And what we found in our graph is that actually every component that we found had a unique sink, so it kind of looked like that. And then of these components, the largest component was the unknot. It had, almost all of the knots that we found edges for were in this one. The second largest was K11 and 34. That's the Conway knot, and it's also so the second largest component had the Conway knot as its sink, and that had 1,673 So there were like, 1.6 thousand knots that were ribbon concordant to the Conway knot. And yeah, so like that's just sort of what this graph looked like. It was just a bunch of components, and then like each, like mostly the unknot component, and each component had like a unique sink. And then I can just sort of tell you about like the obstructions we used, and which ones were useful. I guess like this is so like this is obviously like I'm not even considering the original sample of knots. This is only ones that satisfy Fox-Milner and signature. So obviously like 100% of these knots like were not obstructed by Fox-Milner, but if you count Fox-Milner and slice, that actually obstructs like 99% of the original sample. So these ones, we found that like somehow the best obstruction for us was this Harold Kirk Livingston one. And then that's like the one that's basically it's like a generalization of Fox-Milner, right? It's like the twisted P and Q guys have to have this Fox-Milner condition. And then basically all of the smooth obstructions were like kind of bad and didn't really obstruct anything. So like the tau, epsilon, and mu invariants, they obstructed like 5% of these. Although keep in mind, this is all things that were like definitely not obstructed by the original Fox-Milner, right? So like somehow, anyway, so tau, epsilon, mu obstructed 5%. These, by the way, they're not exclusive. So like the same knot can, like I'm counting it if it's obstructed by two different invariants, I'm counting it under both. S invariant obstructed 5%. Actually, like the 5% obstructed by the S invariant is almost exactly the same as like the 5% obstructed by tau, epsilon, and mu. So like they're like this, is it called symmetric difference when you consider like, anyway, the ones that were only obstructed by one and not the other, there was only like a few hundred of them. So it's like really almost the same set. 6.5% were obstructed by SQ1. So this is the like this generalization of the S invariant, or like this sort of different version of the S invariant for odd Havana homology. So that's actually like, I mean, if you consider this better, I mean, it's somewhat better than the S invariant, a little obstructed like, 20% more knots, right? And then there's one obstruction that is just the Conway knot isn't slice, which obstructs one knot, but really it obstructs like 1,673, right? Because all of the ones that were concordant to the Conway knot are therefore also not slice. And then like so this 1.2% that we labeled as ribbon concordances, that's basically if something is ribbon concordant to something which is not slice, then that original thing also has to be not slice. So this is including like the entire component of the Conway knot, which was only able to be obstructed by like.
For the S invariant, how much of the 5% is from just using F2 or?
I think it was all F2 basically. I don't remember, but like, I mean, I think what we found was that like all like basically tau, epsilon, and mu, and also like the S invariants, they all been essentially like, I mean, I don't remember if it was the same, but like they all essentially obstructed the same like set of knots. Yeah, so and then like there's like 4,000 where we found they were ribbon concordant to something, which was then obstructed, mostly like things like ribbon concordant to the Conway knot, and that gets obstructed. And then there was like there was also SQ. Wait, is my I don't. Okay, I'll just talk loud. So oh wait, it's working again. Okay. SQ1 for even homology. There's also like a version of SQ1 for even homology, and there's also S with rational coefficients. This did not obstruct anything that the other ones didn't obstruct. So I guess like, yeah, they were like just strict subsets. So that's like how useful these obstructions were. And then I guess there's also like another paper that like where that oh, I think I forgot to change some of these numbers. So like this was kind of an older version. But anyway, there's like some other people who are also looking for like computations. They had some way to find ribbon concordances for alternating knots, and they also had some obstructions for alternating knots. So like of like the alternating knots, they were able to find with their method that was like kind of different. They were able to find ribbon disks for like, I think it says 475, but now it's something like 200 something knots that we didn't have disks for, and then we had like 37 knots that they didn't have in with their method. So they just had this method for generating ribbon disks for alternating knots that like is somehow alternating knot specific. And yeah, so like, okay, so I think another sort of computation that we did was, so there's this like approach by Friedman, Gong, Morrison, and Walker to like trying to find a counterexample to the smooth four-dimensional Poincare conjecture, where the method is essentially you want to find a knot K that bounds a disk in like some homotopy force sphere without a ball in such a way that it doesn't bound a disk in the standard B4, because that would prove that your homotopy force sphere is not the standard force sphere. So this is like their sort of method to try to find a counterexample to the smooth four-dimensional Poincare conjecture. And so one thing that we sort of tried to do was like, we tried to see what knots could potentially help go in this direction. And so like specific, like more in particular, Manolescu and Piccirillo constructed some potential counterexamples to the smooth four-dimensional Poincare conjecture. So in this way, so they found that if you have two knots, K and K prime, that share a zero surgery, then, and one of them is slice, and the other is not, then this can be used to construct, like this can be used to do what this Friedman, Gomf, Morrison, and Walker's method asks for. And then they had some method of generating like knots that shared a zero surgery, where it was possible that on one side it could be slice and on the other side it might not be slice. And so they proposed a bunch of pairs like this. They had like this method where you take this thing called an RBG link, and then you like do some stuff and you construct like one of these pairs. So one thing that Nathan and I did was we essentially like tried to construct these pairs like this by brute force, because this like RBG method is like pretty good. You can just definitely construct them. It's like basically you can just draw some links and be like, I'm going to add this number of twists here, this number of twists here, etc., and like just construct one of these pairs. But overall, their pairs tended to be very large. Like on both sides, they tended to be very large. So we were trying to see if we could, by brute force, just like construct pairs like that had shared a zero surgery. Basically, what this meant, what we actually did was like, you can take you can take a knot exterior and then like basically drill holes in it and just like, you can just use this to like construct like some zero surgery to like some other knot, but then like you actually constructed the exterior of the other knot. So you want to like, you want to be able to identify which knot exterior like you constructed. So for this we used Dunfield, Obaden, and Rudd had a program for identifying knot exteriors, where you give it like some triangulated like manifold, which is a knot exterior, and it tells you what the knot is. So using that, we found knots that shared the same zero surgery with a knot of less than or equal to 18 crossings, which was in our sample. I guess like somehow this like so our sample right now is up to 19 crossings, but like of these ones, we were only looking at the 1.6 million ones that were up to 18 crossings that it was 800,000 knots of up to 18 crossings that satisfy the original Fox-Milner and signature zero. You certainly, in order to run this, you certainly have to have your knot satisfy Fox-Milner and signature zero in order to provide one of these potential counterexamples, because like otherwise, like if a knot doesn't satisfy that and is therefore not topologically sliced, then certainly its counterpart, the one that shares a zero surgery with it, will also not be topologically sliced, because like this is like the topologically, like, the point is we're trying to find exotic smooth structures, right? So what we did is we looked at like the knots of 800,000 knots of up to 18 crossings that were like, and then we looked at basically use this to generate knots of the same zero surgery, like that share zero surgery. And then we found like 250,000 pairs, but like most of the time the other knot was very large. So we had like 81,000 where the other knot had less than 100 crossings, and 26,000 of which the other knot had less than 60 crossings. Like you really somehow, like for most of our invariants, you really want the knot to have like less than like, it just like all the invariants start taking a very long time to compute if it's more than like 50 crossings. So, but we like, just if you're okay with taking a longer time, you can sort of go up to 60 crossings. So we looked at this sample where we had like a pair where one knot was, in our sample of less than or equal to 18 crossings, and then the other one had less than or equal to 60 crossings. And then for each of these, so for each of these pairs, we looked at, so for each of these pairs of knots, we sort of tried to look at like whether our original knot was sliced or not, and whether I'm calling it the larger knot because empirically it was always larger, but just like the knot that had shared a zero surgery with our original knot is slice or ribbon. And then like what we found, well, we didn't find any counterexamples to the smooth four-dimensional Poincaré conjecture. Like this is sort of what we found in terms of like the sliceness. So where we're only looking at the ones where the larger knot had less than or equal to 60 crossings. We found that like the base knot, that's like the one that we started with less than or equal to 18 crossings, like this is, I guess, the results. So -1 means not sliced, 0 is we don't know, and 1 means, well, ribbon. And like, so yeah, I guess like you can kind of see that like maybe somewhat possibly interestingly, like there were actually a few knots, like the 0 on the left and 1 or -1 on the right means that we were able to obstruct the larger, or like either construct a ribbon knot or construct a ribbon disk, or like obstruct the larger one, but not the smaller one. So I guess like if you assume the smooth four-dimensional Poincaré conjecture is true, then like we also know like sliceness for, these 11, we know that these 11 knots that in our sample where the larger one is not sliced, obstructed by one of our like, one of these obstructions, like we would also know that those are not sliced. And then maybe somewhat more interestingly, like there were 59 knots where we could find that the larger one we found a disk for. Like the reason I'm saying this is slightly more surprising is that like, the obstructions, like they're like, you can just like sort of do that. Like if there's an obstruction, then the thing is definitely not sliced, right? And you can just compute them like completely. But this method that we had for finding ribbon disks, it like, it's somewhat like it's kind of random whether it's going to work or not, right? It sort of depends on like the picture you drew and whether the bands happen to be like the right bands happen to show up in your picture. We did like one thing we did do is like for each knot that we tried, we did like just sort of shake up the diagram a little bit. So we didn't necessarily start with the minimal diagram before adding the bands. You can just sort of shake it up and be like, I'm going to consider a somewhat larger diagram, but like, and then try to find the bands there. That actually does give you bands that would not show up in like, this is partly because of the way we did the walks. So like one thing about our walk is we never went over the same edge twice in a row in our walk. So like somehow we never did this thing where the band could like loop around an edge, and like, but you can sort of allow that by adding like some Reitermeister 2s to your diagram. So we like, but even so, it's still a little bit like there's some randomness, right? Like you can like a lot of links can just, spans can just not show up. And in general, I would say that this method for finding ribbon disks just works better for smaller knots, right? You're just more likely to find the right band. But apparently for these 59 knots, we could find like a band, we could find the ribbon disk for the larger one and not like our original one. So, you know, if you just assume smooth 4-dimensional Poincare conjecture, then I guess like we have these extra 59 knots in our sample. And then, so this is, okay. So let me just sort of talk about, like I mentioned a bunch of heuristics for behavior. The one thing that like is that we asked about the decrease in complexity. If there's a ribbon concordance from K1 to K2, is K2 just less complicated than K1? This we found was like generally like confirmed by our at least our experiments. So ribbon concordances, they generally dropped volume by a lot. They also dropped like the ranks of like the, you know, of the homologies that we tested, like Havanna homology and HFK and whatnot. They also all like dropped the rank pretty significantly. We didn't really find any where they were like the same. So I guess like at least in our sample, it seems that ribbon concordances do lead to much simpler knots, you know, and also I guess I didn't write this down, but or did I? No, I didn't. Anyway, like I think people don't really talk about this because like number of crossings is not actually a good like, it's not actually an interesting thing for knots, but you know, number of crossings like clearly is some measure of complexity, right? And so what we found was that generally the number of crossings actually dropped a lot. So like the one that dropped the least is probably for 19, if you start with a 19 crossing knot, like the least drop we had was maybe like 14 crossings or something. So like yeah, it's like 19, most of the ones from 19, if we found a ribbon concordance at all, they would be to like 13 crossings or fewer. So like they also dropped complexity in that sense. One thing that we actually didn't expect, or maybe we should have expected, but for whatever reason we didn't, is that we did not find any ribbon concordances from an alternating knot to a non-alternating knot. And like, maybe we should have expected this because like alternating versus non-alternating is at the base level of kind of complexity, right? Non-alternating knots are more complicated than alternating knots. But like, I guess like, yeah, I mean, what happened was one of our friends asked us, like, do you have not like concordances like this? And Nathan and I were like, oh, we have like 1.8 million concordances. Surely we have something like this. And then we looked in our sample and didn't have any. So yeah, so I guess like, but I guess the person who asked this, who was Josh Green, by the way, he probably had some reason to believe that this would be the case. So yeah, we didn't find any ribbon concordances from an alternating knot to a non-alternating knot. Yeah, okay, so there's also like some other folk conjectures that we disproved. I guess I posted a paper with Nathan and also like 3 other authors about this, but you can ask like whether you expect ribbon concordances to preserve the rank of Havanna, of reduced Havanna homology or HFK hat mod 8. And while this seems to be true, like for knots of up to 17 crossings, there are 18 crossing knots that violated this. Recently, Kyle Hayden also found that there's like there are ribbon knots that violate mod 4 also. So so you should not expect things like this, which I guess also kind of shows that, like, you know, yeah. I think he found like HFK mod 4, but I think we like ended up also like we were talking to him and we also found some that were Havanov mod K with mod 4 with his like method. So yeah, so like I guess what this kind of shows is like up to 17 crossings is not a lot, and like in some sense neither is 19 crossings, right? Because that's only 2 more than 17. So like really, like, you know, like it is like things that we found also don't necessarily just like, you don't necessarily expect this to hold, because like 19 crossings is in some sense still very small. And then I guess, like, as I mentioned earlier, like another thing that maybe confirmed previous expected behavior was that like every component in this graph had a unique sync. And okay, I think I'll stop here. Thanks.